Now, based on the type of environment, it is important that exploits be classified into different types. That helps the penetration tester to accommodate several variables in a penetration test, which helps him to conduct a thorough penetration test. Exploits are generally categorized using the following criteria, such as the type of flaw that is taken advantage of, such as BOF or dangling pointer, remote or local. Remote exploits refer to vulnerabilities which can be exploited from a network remotely, while local exploits need to be executed on the same machine. RCE are more important and critical than local exploits since user interaction is almost removed. The result of the exploit. Some of the examples being denial of service and remote command execution. Stack-based exploit is dependent on a stack-based buffer overflow, which occurs when data more than the stack space has been filled out. The data from the stack is replaced by specifically crafted values by the attacker, which enables it to redirect the program execution process to the malicious code, which in most cases is shellcode, which spawns a terminal interface which allows the attacker to execute remote commands to the target device. The data stored in a heap is through functions which dynamically allocate memory, such as malloc. As we know by now, heap is first in first out and it grows towards the higher memory address in the memory. When an attacker enters the data in heap, it overflows the adjacent data that is in the lower part of the heap. If any application takes an input from the user and copies it in the memory without checking it, a heap overflow may occur. And most of the times, it can also result in arbitrary code execution due to data entered by the attacker, resulting in compromising the application and the system. Some other types of exploits include format string and integer bug exploits, which are widely used to test applications. Format string exploits are used to crash software or to execute malicious code through string type crafted input. This attack is possible because the user input is filtered as a format string parameter in several C functions that perform formatting, such as printf. A malicious user may use the %s and %x format tokens, among others, to print data from the stack or possibly other locations in memory. Integer bugs are exploited by passing an oversized integer to integer variable. It may cause overwriting of valid program control data, resulting in execution of malicious codes. Integer bugs are very often found and exploited in applications to achieve various purposes. Continuing with the classification of exploits, here we shall see about remote and local exploits. Remote exploits are those exploits which can be executed on the remote system. For example, a FTP server taking a malicious input from a client machine, resulting into a buffer overflow which gives access to whole server. Remote exploits tend to exploit the services running on the system to gain access to the systems. They are generally non-root and not system services. Remote exploits are carried out over a network. Local exploits are those exploits which can only be executed on the local machine, where the vulnerability has been found and cannot be mutated to a remote exploit. Local exploits usually exist in the applications that are locally installed on the system and results in privileges escalation. In this slide, we shall discuss the process of writing an exploit. For the sake of clarity, I will list the steps in a sequential manner. The steps are as follows. Identify and analyze application for any vulnerability. Next, attach it with a debugger and check whether the return value can be overwritten by providing input to the vulnerable application. Next, in case of success, automate the process using a scripting language, preferably Perl or Python, to make the work easier. And the final step would be to check the dynamic link libraries loaded onto the RAM and try to find an address where shellcode can be injected to redirect the program execution flow to the desired place. This, by no means, is a detailed process, and the steps may have several divisions, but the overall process can be summed up as such. Now, shellcodes are an integral part of the testing process and are extremely essential to constitute proof of concepts of vulnerabilities. Shellcodes are a set of instructions which use system calls and are used by exploits for carrying out some actions on client machines. They are executed after a vulnerability is exploited, and they are working machine instructions in a character array within an exploit source code. They are operating system dependent as we have different system calls in different operating systems. Even in Windows itself, different service packs are involved in different system calls. Shellcodes are machine instructions which are used to directly process via the desired instruction at memory location. As we are nearing the end of this module, the final discussion will be about the construction of shellcode. Once again, for the sake of clarity, I shall attempt to list out the process in a sequential manner. The steps of writing a shellcode are as follows. Write the code in assembly language or in C language and disassemble it using GDB or OLEDBG. Get the argument and system call IDs for the operating system you are targeting the shellcode for. Convert the assembly codes into opcodes and eliminate null bytes from it. Next would be to compile it and execute. Finally, inject the running code into the previous working exploit to check if it is working or not.